Welcome! In this session, we'll explore a fascinating geometry problem titled Check if it is a straight line. We'll analyze the approach to determine if a given set of points lies on a straight line. Let's dive into the problem and break it down step by step for clarity and understanding. In this problem, we are tasked with determining if a series of points on a 2D plane all lie on the same straight line. Each point is represented as a pair of coordinates, x, y, in the input array called coordinates. For example, consider the first example input where the points are 1 2, 2 3, 3 4, 4 5, 5 6, 6 7. The output here is true, which means these points do lie on a straight line. To verify this, we can calculate the slope between consecutive points. The slope between the first 2 points, 1, 2, and 2, 3, is calculated as the change in y divided by the change in x, or 3, 2, / 2 to 1 equals 1. Similarly, the slope between 2, 3, and 3, 4 is also 4, 3, / 3 to 2 equals 1. Since all pairs of consecutive points have the same slope, we can conclude that all the points lie on the same straight line. Now let's examine another example. Here, the input coordinates are 1 1, 2 2, 3 4, 4 5, 5 6, 7 7. This time, the output is false. This indicates that the points do not form a straight line. To understand why, we can again calculate the slopes between consecutive points. Starting with 1 1 and 2 2, the slope is 2 1 / 2 to 1 equals 1. However, the slope between 2 2 and 3 4 is 4 2 / 3 to 2 equals 2. Since the slopes are inconsistent, the points do not align on the same straight line. This demonstrates that for a set of points to form a straight line, the slope between every consecutive pair of points must remain the same. In the third example, the input is 0 0, 0 1, 0 1, and the output is true. This means the points do lie on a straight line, but in this case, it's a vertical line. Vertical lines have an undefined slope because the change in x is 0, resulting in division by 0. However, we can still confirm that the points are aligned by checking if all the x-coordinates are the same. Here, all the x-coordinates are 0, so the points form a vertical straight line. This demonstrates that even in cases where the slope is undefined, the points can still form a straight line if a consistent pattern exists. Now let's consider some important constraints and edge cases. The input array will always have at least 2 points, and if there are only 2 points, the output will always be true because any 2 points can form a straight line. For vertical lines, where all x-coordinates are the same, or horizontal lines, where all y-coordinates are the same, the function should handle these special cases explicitly. Additionally, the solution must handle points with mixed positive, negative, and 0 coordinates correctly. Finally, with up to 10,000 points in the input, it's crucial that the implementation is efficient and performs well even for the maximum constraint. Ensuring these considerations will make the solution both correct and robust. To determine whether a set of points lies on a straight line, the key idea is to verify if the slope between any 2 points remains consistent across all the points in the dataset. We can approach this in a few different ways. The first is the brute force approach. Here, we calculate the slope between every pair of points, compare each slope to the first calculated slope, and check if they are all equal. This method uses 2 nested loops, making it straightforward to implement. However, it becomes computationally expensive as the input size increases, with a time complexity of n². Additionally, it doesn't require extra space, so its space complexity is 1. Despite its simplicity, this approach is inefficient for larger datasets, especially when the number of points exceeds 1,000. A more efficient alternative is the optimized approach using a fixed slope. In this method, we calculate the slope using just the first 2 points and then verify that this slope remains constant for all other points. Instead of relying on division, which can lead to precision issues, we use the cross-product formula to check for collinearity. This avoids errors and ensures robustness, even in edge cases like vertical lines. In the optimized approach, after calculating the initial slope using the first 2 points, we iterate through the remaining points and verify that the relationship holds using the cross-product condition, y2, y1, asterisk, x3, x2, equals, y3, y2, asterisk, x2, x1. This method is highly efficient, with a time complexity of O(n), as we only iterate through the points once. It also has a space complexity of O(1), as no additional data structures are needed. This approach stands out because it avoids division, reducing the risk of precision issues, and handles special cases like vertical lines seamlessly. Another method worth considering is the vector cross-product approach, which involves using vector mathematics to determine if consecutive vectors formed by the points are parallel. This is done by computing the cross-product of vectors generated by 3 consecutive points. If the cross-product is 0 for all consecutive points, the points are collinear. While this method is mathematically elegant, it can be more challenging to implement and debug, particularly for those new to the concept of vector operations. It also has a time complexity of O(n) and a space complexity of O(1), making it an efficient but more advanced solution. The optimized approach using a fixed slope was chosen as the best strategy because it combines simplicity, efficiency, and robustness. By avoiding division and using the cross-product formula, it gracefully handles edge cases like vertical lines and eliminates potential floating point precision errors. While the vector cross-product approach is equally efficient, it's less intuitive and harder to implement, making it less practical for this specific problem. The brute force approach, while easy to understand, is computationally prohibitive for larger inputs and was therefore not selected. The key observations that support our chosen strategy include the fact that the slope between 2 points remains constant only if the points lie on the same straight line. By avoiding division, we minimize precision-related issues, and the problem reduces to verifying a single condition iteratively. This makes the solution not only efficient, with a time complexity of O(n), but also easy to understand and implement. Overall, the optimized approach strikes the right balance between clarity, efficiency, and robustness, making it ideal for both competitive programming scenarios and real-world applications. To determine if a set of points lies on a straight line, we begin by understanding the mathematical foundation. 2 points, say, x1, y1, and x2, y2, lie on the same straight line if the slope between them remains constant when compared to the slope of any other pair of points. The slope formula is y2 y1 / x2 x1, but instead of directly dividing, we use a more reliable method, cross multiplication. This avoids floating point precision issues. So, instead of comparing slopes through division, we check if the cross products are equal. Specifically, we verify if y2 y1 asterisk x3 x1 equals y3 y1 asterisk x2 x1 for any other point x3 y3. Next, we validate the input. If there are fewer than 2 points, we simply return true because any set of fewer than 2 points is trivially collinear. Finally, we pre-compute the reference slope using the first 2 points. Let dy equals y2 y1 and dx equals x2 x1. These values will serve as the basis for comparison with all subsequent points. Now, we move on to iterating over the remaining points. For each additional point, x3, y3, we calculate the slope relative to the first point, x1, y1, using the cross-multiplication method. Specifically, we check if dy asterisk x3 x1 equals dx asterisk y3 y1. If this condition fails for any point, it means that the points do not lie on the same line, and we immediately return false. On the other hand, if all points satisfy the condition, we return true at the end. There are a few key insights to highlight here. First, cross-multiplication ensures precision by avoiding floating point inaccuracies. Second, the algorithm is optimized with an early exit. If any point fails the condition, we don't waste time checking further. Finally, by pre-computing the reference slope using the first 2 points, we avoid redundant calculations, improving efficiency. To implement this algorithm, we use simple and efficient data structures. The input list of points is stored as a list of tuples, like x1, y1 is x2, y2, allowing easy indexing during iteration. For the slope calculations, we use basic variables to store the reference differences dx and dy, keeping memory usage minimal. Let's break down the key operations involved. Pre-computing the slope with the first 2 points is a one-time operation and takes constant time, O(1). Then, iterating through the remaining points involves checking each point against the reference slope, which is an O(n) operation for n points. Each slope comparison itself, using cross-multiplication, is a simple arithmetic operation that runs in O(1). This streamlined approach ensures the algorithm is efficient both in terms of time and space usage. When working with this algorithm, it's important to account for edge cases to ensure robustness. One key scenario is collinear points with a vertical line, where all x values are the same, resulting in an infinite slope. The algorithm should handle this gracefully using the cross-multiplication method. Another situation is when there are duplicate points, which must not disrupt the slope calculations. Additionally, we need to verify how the algorithm behaves with minimal input, such as just 2 points, which should always return true. Lastly, the algorithm must efficiently handle large inputs, up to the maximum constraint of 10⁴ points. Now for the complexity analysis. The time complexity is O(n), because we compare each point against the reference slope exactly once. The space complexity is O(1), as no additional data structures are used beyond the input and a few variables. This makes the algorithm both scalable and resource efficient. This Python implementation solves the LeetCode problem number 1232, check if it is a straight line. The goal is to determine if a set of points in a 2D coordinate plane all lie on the same straight line. Step-by-step explanation. 1. Extract the first 2 points. The algorithm starts by extracting the first 2 points from the coordinates list. These points define the initial slope of the potential straight line. 2. Compute the slope using cross-multiplication. Instead of directly calculating the slope as a fraction, dy/dx, the solution uses cross-multiplication to avoid division by 0 errors. Specifically, the slope between 2 points, x1, y1, and x2, y2, is represented as the ratio of their differences in y, dy, and x, dx. 3. Iterate through the remaining points. For each subsequent point, the algorithm checks if the slope between the first point, x1, y1, and the current point matches the initial slope. This is done using the formula white y1 dx x x1 dy. If this condition is violated for any point, the function immediately returns false, indicating that the points do not lie on a straight line. 4. Return true if all points align. If the loop completes without finding a mismatch, the function returns true, confirming that all points lie on the same straight line. Edge cases. Minimum input size, with only 2 points, the function automatically returns true since 2 points always form a straight line. Vertical lines, the use of cross-multiplication ensures that vertical lines, where dx = 0, are handled correctly without division errors. Floating point precision. By avoiding direct division, the algorithm sidesteps potential floating point precision issues. This implementation is efficient with a time complexity of O(n), where n is the number of points, as it iterates through the list of points once. It also has a constant space complexity, O(1), as it uses only a few variables for calculations. This makes it a robust and optimal solution for the problem. This is the Java implementation of LeetCode problem number 1232, check if it is a straight line. The solution mirrors the logic of the Python implementation by calculating slopes using cross-multiplication to avoid division. The method iterates through all points to confirm they lie on the same straight line. Key differences include Java-specific syntax, such as type declarations for inputs and variables, and the use of arrays for coordinates. The algorithm ensures efficiency while maintaining clarity. To determine if the given points lie on a straight line, we start with the first 2 points. Here, the first point is 1, 2, and the second point is 2, 4. Using these, we calculate the differences. Dx, which is the difference in the x-coordinates, is 2 minus 1, giving us 1. Similarly, dy, the difference in the y-coordinates, is 4 minus 2, which equals 2. These values represent the slope between the first 2 points. Next, we verify if the remaining point, 3, 6, aligns with this slope. For this, we calculate the differences relative to the first point. The x difference is 3 minus 1, and the y difference is 6 minus 2. Using cross-multiplication, we check if y1 multiplied by dx equals x1 multiplied by dysprosium. Substituting the values, we get 4 times 1 equals 2 times 2. This simplifies to 4 equals 4, which is true. Since all points maintain the same slope, the points are on a straight line, and we return true. Now, let's consider another example to test if the points lie on a straight line. The coordinates are 1, 1, 2, 2, and 3, 4. Again, we start with the first 2 points. For 1, 1, and 2, 2, we calculate dx as 2 minus 1, which is 1, and dy is 2 minus 1, which is also 1. This gives us the slope between the first 2 points. Now, we check the third point, 3, 4, relative to the first point. The x difference is 3 minus 1, and the y difference is 4 minus 1. Using cross-multiplication, we check if y1 multiplied by dx equals x1 multiplied by dysprosium. Substituting the values, we get 3 times 1 equals 2 times 1. This simplifies to 3 equals 2, which is false. Since the third point does not follow the same slope as the first 2, the points do not lie on a straight line, and we return false. Lastly, let's examine a case where the points form a vertical line. The given coordinates are 2, 1, 2, 3, and 2, 5. Starting with the first 2 points, we calculate dx as 2 minus 2, which is 0, and dy is 3 minus 1, which is 2. This indicates a vertical slope, as the x-coordinates remain constant. Now, we verify the third point, 2, 5, to see if it aligns with this slope. The x difference is 2 minus 2, and the y difference is 5 minus 1. Using cross-multiplication, we check if y1 multiplied by dx equals x1 multiplied by dysprosium. Substituting the values, we get 4 times 0 equals 0 times 2. This simplifies to 0 equals 0, which is true. Since all points maintain the same vertical slope, they are aligned, and we return true. To analyze the time complexity of this solution, we begin with the initialization of variables. Extracting the first 2 points, x1, y1 into x2, and y2, and calculating the differences dx and dy are both constant time operations, or O1. Next, we move to the iteration over the remaining points in the coordinates list. Here, the loop runs from the third point to the nth point, leading to n2 iterations in the worst case. Within each iteration, we compute the left-hand side and right-hand side of the equation to check if the current point lies on the same line. These calculations involve basic arithmetic operations, each of which is O1. When we sum up the cost of all iterations, the total time spent in the loop becomes O(n)(2), which simplifies to O(n). Adding the constant time initialization to this, the overall time complexity of our algorithm is dominated by the linear iteration, resulting in O(n). Now, let's consider the space complexity. The algorithm is highly space efficient, with a space complexity of O(1). This is because it does not use any additional data structures or dynamic memory allocations. The input, the coordinates list, is provided to the function, so its storage is not counted towards the algorithm's space usage. The only memory required is for a fixed set of variables such as x1, y1 is x2, y2, dx, dy, and the temporary variables x and y used during the iteration. Since the memory needed for these variables does not grow with the size of the input, it is constant. Therefore, the overall space complexity remains O(1), making the solution highly space optimized. When comparing this approach to a brute force or naive method, the efficiency becomes even more apparent. A naive approach might calculate the slope between every pair of points and check for consistency. With n points, this would involve n1/2 pairs, leading to a time complexity of O(n²). Additionally, storing all pairwise slopes would require O(n² space. In contrast, the optimized solution reduces time complexity to O(n) through a single iteration and space complexity to O(1) by avoiding additional data structures. The mathematical reasoning behind this is straightforward. The O(n) time complexity comes from iterating through the points once, while the O(1) space complexity is due to the constant number of variables used. Whether in the best, average, or worst case, the algorithm consistently operates in linear time. Even if the points do not form a straight line, the worst-case analysis still considers the maximum input size, keeping the time complexity O(n). To summarize, this solution is both time and space optimal for the problem. With a time complexity of O(n) and a space complexity of O(1), it strikes a perfect balance between efficiency and simplicity. The use of cross-multiplication avoids division operations, ensuring numerical stability and making the solution robust. Compared to the naive approach, this method is significantly faster and uses much less memory, making it ideal for handling even large datasets. This combination of performance and precision highlights the effectiveness of the optimized approach. When solving this problem, there are several common mistakes you should be aware of. First, an incorrect slope calculation often occurs when handling vertical lines. In these cases, the slope is undefined because division by zero is involved. This must be handled explicitly to avoid runtime errors or incorrect results. Another common issue is floating point precision errors. Directly comparing slopes using floating point arithmetic can lead to inaccuracies due to how computers store decimal numbers. A better approach is to use cross-multiplication, which avoids division altogether. Additionally, it's a mistake to assume that only the first 2 points need to be checked against the rest. Instead, all points must be verified to ensure consistency across every pair of points. Finally, edge cases such as having only 2 points or all points being the same are often overlooked. These cases should be addressed explicitly as part of your solution to ensure robustness. Now, let's talk about inefficiencies and how to optimize your solution. One common inefficiency is using a nested loop approach with O(n)² complexity to check slopes between all pairs of points. While this may work for small inputs, it can cause time limit exceeded errors for larger datasets, especially when n exceeds 10,000. Instead, focus on optimizing by checking relative slopes in a single pass. When interviewing, remember that the core of this problem lies in verifying the consistency of slopes. Using cross-multiplication not only avoids floating point issues but also simplifies the logic. For large inputs, you might want to discuss optimization strategies, like pre-computing values or leveraging data structures to reduce complexity. Additionally, discussing edge cases like vertical lines, duplicate points, or scenarios with just 2 points demonstrates thoroughness. If asked follow-up questions, be prepared to extend the discussion to variations, such as finding the largest subset of collinear points or adapting the solution for different geometric constraints. This problem shares connections with a few other computational geometry challenges. For instance, LeetCode 149, max points on a line, involves finding the largest number of collinear points, making it a more complex variation. LeetCode 1232, the problem at hand, is a simpler version focused solely on checking collinearity. Another related problem, LeetCode 587, erect the fence, involves finding the convex hull of points, which is a fundamental concept in computational geometry. While not directly related, LeetCode 451, sort characters by frequency, can provide useful insights into sorting and optimization techniques that might be helpful for tackling geometry problems. As for alternative approaches, you could use the vector cross product to determine collinearity. This avoids division and floating point issues but requires careful handling of large integers. Sorting points by their angular relationship to a reference is another method, though it adds O(n) log n) complexity. Lastly, hashing slopes relative to a fixed point is ideal for finding subsets of collinear points but introduces potential memory overhead. Each of these techniques has trade-offs, so choose the one that best fits the problem's constraints and requirements. Great job! To wrap up, we've learned how to determine if points lie on a straight line by checking for consistent slopes between pairs of points. This method combines geometry with simple programming concepts. Thanks for watching, and don't forget to like and subscribe for more insights into coding problems. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!